In this problem, we have a speeder in a car that passes a police car. The speeder is driving at a constant velocity of 100 miles per hour. It takes the policeman 3 seconds to react, at which time he accelerates the police car at 20 feet per second squared, until he reaches a maximum velocity of 120 miles per hour. The police car continues to travel at 120 miles per hour until it overtakes the speeder. Starting from the point where the speeder passes the police car, what distance does the police car have to travel before it overtakes the speeder? All right, so there's a lot of information in this problem. We know that the speeder has a constant 100 miles per hour speed. So that means the acceleration of the car is 0. The reaction time of the policeman is 3 seconds. The policeman accelerates at 20 feet per second squared, which is constant, until he reaches a maximum 120 miles per hour. And we want to find the distance that the police car has to travel before it overtakes the speeder. So we're given some information about acceleration and velocity. So we're going to use that to find information about position, and then we'll set the two positions equal, the one for the car and the one for the policeman, to find out how far the policeman has to travel. So first, we want to get familiar with the problem and draw the graphs, right? Because graphs are really helpful. So we're going to do acceleration time, velocity time, and position time. This is an erratic problem because there are several different regions, so we're going to identify those. All the accelerations in this problem are constant, so we'll use the constant acceleration equations to find unknown variables. And then we'll set the positions equal between the car and the policeman. All right, so first we want to draw graphs. So up here we have the acceleration graph of the policeman, right? Because the car has no acceleration. So it takes him 3 seconds to react, then he accelerates at 20 feet per second squared, then travels at a constant velocity until he catches the car. All right, so down here, the policeman has no velocity until it reacts, and then increases its velocity. The slope of this would be 20, and then travels at its maximum velocity. The car has a constant velocity, so it doesn't change. Position for the car is linear because it has a constant velocity, and the slope of this line would be the value of that velocity. For the police car, no change in position until the reaction time. Then it increases its position non-linearly, and then it goes linear after that. All right, and we have the different regions, right? We won't worry about the reaction time region because we're not going to do much with it. So region 1, region 2. All right, all the accelerations are constant. The car has 0, and the police car has either 0 or 20 feet per second squared. So these are the constant acceleration equations we can use. All right, so we do not know how long it takes the policeman to get up to its maximum speed, Tmax. We don't know the final time either. So those are two unknowns. But we know some things about the acceleration and the velocity. So if we look at the equation, what equation has velocity, acceleration, and time? Well, the first one does. So we will use this to find the missing time. All right, then once we have the time, we need to find information about position. So what equation has position, velocity, and acceleration in it? Well, the second one. So we'll use that to find positions. All right, so let's start with the velocity. All right, we're going to find the time it takes for the police car to reach its maximum velocity. We're going to use the equation indicated. Plug in at time Tmax, right? So we have the velocity max, the initial velocity of the police car, which is 0. The acceleration of the police car, Tmax, minus T reaction, right? Because the initial point that we're working with is at this t reaction, right? Not at time t equals 0. All right, so we plug all that in, and we find that it takes the police car 11.8 seconds to reach its maximum speed. All right, so position, we're going to use the position equation and plug in at the final time. So for the car, we're going to do the car first. So the final position of the car, initial position of the car, velocity of the car, and the times. So for the car, the time at t0 is 0, right? Because it starts at 0. All right, then we get an equation for the position of the car. All right, so we're not going to do anything with that right now. We'll just label it and use it later. Then we can move on to the policeman. The policeman has segments, so we'll do segment 1 first, and then segment 2 after. We use the same equation, plug in at Tmax, so we're going to plug in at this point. Our initial point is T reaction, so we plug in all of those variables, right? Initial position 0, initial velocity 0, and then we get the position of the police car when it reaches its maximum velocity is 774.4 feet. All right, then we move on to segment 2, use the same equation. Now our 2 points are Tmax and Tfinal. So we plug those in, and we get an equation for the position of the police car. So note that the initial position is the position that we calculated above, right? The 774.4 feet. All right, now we have another equation. So we have equation for the position of the car and equation for the position of the policeman. So we're going to equate those two. So they'll be equal when the police car catches up, and solve for T final. Then we can take that T final and plug it back into either equation 1 or equation 2. And we find that it takes 1.23 miles for the police car to catch up.